Hello, I'm James Ashball, and this is Lab 3, Black Hole and Orbits. The overall big picture is that in both Part 1 and 2 of this lab, we are examining the force of gravity and its relationship with orbits in space. Specifically, in Part 1, we are calculating the unknown mass of a black hole given a unique trajectory of an orbiting object. In Part 2, we are finding a starting velocity for a spaceship that will cause it to orbit a two-object system, the Earth and Moon, in a figure-8 trajectory. Some underlying physics principles are the force of gravity, the velocity update formula, and the position update formula. Here is a brief preview of the results for both parts of the lab. In part 1, I was successfully able to calculate the mass of the black hole to be 5.05965 times 10 to the 28th kilograms. In part 2, I was able to find an initial velocity of 2.44 times 10 to the 4th, 2.44 times 10 to the 4th 0 meters per second for the ship for it to successfully orbit the planet and the moon without crashing. For part 1 setup, the system is a star, while the surroundings are the black hole, and the initial conditions shown on the right place a star moving with an initial trajectory. Code of part 1, I first calculated the perpendicular and parallel components of the star's change in momentum over time. I then added the components together to find the net force acting on the star. Finally, I used the result to calculate the mass of the black hole. As a result, I found the mass of the black hole to be 5.05965 times 10 to the 28th kilograms. The output of the star's trajectory is on the right. For 2 setup, the system alternates depending on what you are analyzing, choosing one of the 3 masses, and the surroundings are the other 2 masses outside of the system. The initial conditions shown on the right are that the ship launches with an initial velocity from the moon's surface. For the code of part 2, I calculated the net force on the moon and the ship using the force of gravity equation, and then updated the ship's position and velocity every time step, as shown by the code on the right. For the results of part 2, I found the ideal initial ship velocity to be 2.44 times 10 to the 4th, 2.44 times 10 to the 4th, and 0 meters per second, and the output of the ship's trajectory, as shown on the right. Some overall possible error sources and similarities and differences to real life include the presence of a time step, which makes instantaneous data of position and velocity difficult to find, and specifically, to part 2, the initial velocity is slightly off from ideal, causing the ship to not have a perfect figure-8 orbit around the moon and planet. So what does it mean relating to part 1? The difference between rate of change in momentum and its parallel and perpendicular components is that the sum of parallel and perpendicular components of change in momentum over time equal the net force on that object, while in comparison, the rate of change of momentum is how fast the net force on the planet in part 1 is changing. What if relating to part 2? In predicting the motion of the entire system, you would need to calculate the net force on the planet and the black hole, as well as what we have done, which is calculate the net force on the ship and moon. Because of the black hole's large mass, as well as the planet, the interactions between the black hole and planet will be more dominant. This is the primary interaction which causes the planet, moon, and ship to orbit around the black hole. In conclusion, you can utilize the force of gravity equation to predict data about planetary orbits. You can also use the velocity and position update formulas to update the position and velocity of an object every time step. Thank you.